Hello, everyone. Good to see you again. Good that we're together again. There's, in this particular discussion, or related to this particular discussion, I'm looking at making probably no more than 4 videos, possibly less than 4 videos, discussing these 4 topics, because there's a relationship between all of them. So it's likely going to be 4 videos, and this is the first of the 4, of the at most 4, I think. I guess you could say it like that, as we're doing this whole thing in a preliminary sense. Here is the situation. Today we're going to look at some probability theory. A look at some probability theory today. That's topic 1. On another day, we're going to look at topic 2, Wallace's formula for pi. Then we're going to look at topic 3 some other time. Perhaps we'll combine these. We'll see how the time runs on all these. Then we're going to look at Stirling's formula. And 4, we're going to look at the normal distribution, some aspects of it, a derivation of the normal distribution. To get a good derivation of the normal distribution, to get the derivation of the normal distribution, you need to look at some probability, be aware of certain aspects of probability relatively strongly. You want to be aware of some aspects of probability theory. And then you also want to know a formula for pi, known as Wallace's formula. And you want to know something that is related to an approximation to the factorial function of factorials. Approximation of factorials, an approximation of factorials is Stirling's formula. Those 3, a look at some probability theory, Wallace's formula for pi, Stirling's formula, those 3 give us much of the basis that we need to talk about the normal distribution. So, and it's a good idea to go in this order, I believe, because we build up to the normal distribution, and the 3 things prior to topic 4, a look at some probability theory, Wallace's formula for pi, and Stirling's formula, build us up to here and get us there. So these 4 are pretty interesting. And that's what we're going to try to do. Today, as we said, it's just going to be a look at some probability theory, and that's that. Afterwards, Wallace's formula for pi, Stirling's formula, and then the normal distribution. So whenever that gets done in the videos that we're doing, that's kind of a general game plan for what we want to do. So, a look at some probability theory. What do you want to say about it? What can we say about it? Well, and then at the end of, let me say another thing. At the end of each of the videos, and again, I haven't decided how many videos are going to be. It's going to be 4 videos, but they might get sandwiched together into like maybe 2 long videos, or maybe it's going to be 4 videos separately. Regardless, there is going to be the hard copy presentation from which I'm working there. A look at some probability theory. We'll scroll at the end of each video that's pertaining to this. A look at some probability theory is going to scroll at the end of each of those videos. It's going to be composited, put together with another article, Wallace's formula for pi, and again, those 2, as they're composited together, are going to be composited with Stirling's formula, and at the end, they're all going to be composited with the normal distribution. So everything that I'm talking about, if you want to look at it, hard copy more or less, the people who have me as a teacher, as I'm formally trying to teach, I guess you could say, where we're trying to learn this stuff, they already have access to the hard copy. So this is going to be in the video as well, for everybody to have access to the hard copy as well when we're doing this. So that's it. You'll see that. You'll see one big article composed, one big article composed of these 4 articles right here. They're going to be right here. One big article composed of those 4 articles. So, all right. Let's talk a little bit more about this. There's some good references, and again, you'll see this as they scroll down. I use a lot of stuff from, there's some great references that were immensely helpful to me, and there are many other references not mentioned that were also amazing. Sokolnikov and Redheffer, Mathematics of Physics and Modern Engineering, 1966, was an excellent resource. Sokolnikov, again, same author from Sokolnikov and Redheffer. Sokolnikov, from a 1939 book called Advanced Calculus, also has some great references there as well. Ostrowski, Differential and Integral Calculus, 1968, Volume 1, also excellent. Courant and John, Introduction to Calculus and Analysis, Volume 1, originally published 1965, copyright 1985. And again, you'll see all this stuff. Those were all very useful. There are some other references. Golay, last name Golay, Michael, Convergence of Binomial and Normal Distributions for Large Numbers of Trials, fall 2004. There's an HTTPS location where people can look at that. I think it's online courses and stuff like that, or online material associated with MIT, I believe. Turner, James E., Atoms, Radiation, and Radiation Protection, and they talk about, he talks about some stuff as well that I was able to use here. All right, there's a lot here. We proceed throughout the rest of this presentation, or at least to start the presentation, I guess you say the rest of it as well. First of all, you got to give credit where credit's due, you guys. These are great resources. This stuff does not get done without great resources. Nobody really does anything by themselves. You can't do it. You got to learn from others. You got to stand on other people's shoulders to do something like that. Absolutely, I would have had a very difficult time, if not a time. I wouldn't be able to do this without some of the resources that I consult. And that's generally true for everybody. We got to learn from one another, I guess you could say, right? We proceed throughout the rest of this presentation to look at some amazing equations and conclusions which are remarkable in and of themselves, you guys. That's pretty important in itself, but which also lead us to the very important normal distribution. As I said, you're running through this, you're running through these topics, these three topics, and that leads us to the very important normal distribution. There's still other things you have to do to get to the normal distribution, but I think these three right here really give you a strict foundation that's good to look at. It's good to know why something's true, guys. It's a very important aspect of what we do in our work. Why is something true? Why is this working? So these three give us a very strong, you can even say intuitive foundation if we look at them very carefully. It gives a very strong foundation to approach this right here, and then we proceed further, and we indeed get this right here, the normal distribution. Okay. That's the goal. All of the aforementioned sources were of immense help in looking at these matters. Absolutely. Hopefully this is of some benefit to people, and we'll take it from there. Obviously, I could not have done it without looking at some of this stuff. So hopefully it's going to be worth your while, you guys, to look at it. Let's look at the binomial theorem and binomial coefficients and see what we can say, and we'll kind of take it from there, I guess you could say. So as we say this, so let's make sure, guys, I've got, okay, I want to make sure I can be heard here, guys. All right, guys, so we've got this. We know what we're looking out for with roughly at most 4 videos coming our way. This is the first of the at most 4 videos, and it pertains to this, and that's what we wrote right here. Let's erase this, and let's talk about some of the stuff pertaining to our look at some probability theory. Eventually, this is going to get erased as well, guys, pretty soon, I think. But let's see what we got, what we can say. They talk about the binomial theorem and binomial coefficients, and I just think this stuff is good to have in our back pocket as we're proceeding in much of the study of what we're doing. It's just good to have. It's good to have these tools. It's good to have this machinery, so to speak. So the binomial theorem and binomial coefficients goes as follows. Write it out a little bit. And let's see what we can say here, guys. And the coefficients tell us a whole lot. I mean, if we associate it the right way, I guess you could say. So as we're looking at this, if you were to take a plus b to the n power, n is a positive integer, not necessarily it's an integer greater than or equal to 0, the way we can do this. That right there, if you were actually trying to evaluate that binomial taken to the nth power, it's a summation from k equals 0 to n is the same as the n right here, of n factorial over k factorial, the quantity n minus k. The quantity n minus k factorial a to the n minus k, b to the k. Also note that Sokolnikov and Redheffer that the probability of our successes in n independent trials is this. So let me try to tie this up, kind of using some of the notes here. They're a little bit. There's a little bit of divergence in terminology sometimes, or at least in symbolism. So let's kind of just point it out. That's n factorial over r factorial, n minus r factorial. So, and this is p, probability of one success, or probability of success of one success. That's just the p. You take it to the r, and q is the probability of failure. That's n minus r. So p is the probability of success, and q is the probability of failure. And look, there's one of two things that are going to happen for our purposes, and it's pretty intuitive, I guess you could say. There's p probability of success. Zero probability means impossible. Probability 0 means impossible. Impossible is what 0 probability means. And probability of 1 means certainty. And, well, there's one thing for certain. There's two choices. There's a probability of success, and there's a probability of failure, and we know that one or the other is going to happen. What does that mean? Well, if you add these two probabilities together, P plus Q, yeah, it's certain one of them is going to happen. There's going to be a success or there's going to be a failure, and that's for sure. This right here, you guys, is essentially the probability of our successes out of a total of n trials. N is the number of trials, R is the number of successes, and how does that play out? Well, what would be out of n trials, what's going to happen? Well, I don't know. In n trials, there may be no successes. Look, the more you try, the more chance there is there's going to be at least one success. To get a lot of successes in a row, it's a little tougher. But this kind of talks about it. So this thing's basically the probability of our successes out of n trials. And this plays into it. For each one of the n trials, you want to know how many times, for there to be a success, there's R number of successes. Well, P to the R means P times P times P times P, R times. So there's R successes. Okay, yeah, there's N minus R failures, for sure. Every single scenario when it can happen. Look, you do this in order, but yeah, the order could be all messed up. I mean, you could draw, and the first R drawings that you make, or the first R attempts that you make, are all successes, and then the last N minus R attempts are all failures. Yeah. Or the first N minus R attempts are all failures, and then the last R are successes. But whatever, or they could all be mixed in there together. But this is all the probabilities of it one time happening, and you look at how many ways the combinations tell us. These are about combinations. This is combinatorics right here. These are the number of combinations that are allowed. Order matters. Actually, order does not matter. Once you actually, it doesn't matter, I guess you could say. When something is situated in a particular way, you don't, within that arrangement, you don't switch around within that arrangement. That arrangement occurs once, and that's it. If you were talking about permutations, this R factorial would not be there. It'd be the number of permutations that you need. This is the number of combinations to give us the probability. So this is where we're at. It's talking about something like this, you guys, to get us to where we got to go. If you think that, forget the summation symbol right here for a second. If you think that this, all this, and that, well, if you took the B to the K right here, and the A to the N minus K, put it over there. Doesn't matter the order that you multiply. If you replace the R by a K, you basically got the same thing if you just get rid of this guy. If you were to add every possible way this could occur, from R being 0 successes all the way to N successes, if you added them together, you would be adding this. And you know what that means? That would be certainty. For certain, you'd get one of those arrangements. One of those arrangements, how many of them are there? Yeah, well, there's quite a few. I mean, however many times you're going to be doing that to actually get it there. That's some pretty interesting stuff in its own right. But if you added just all of these right here with this guy, this would tell you how many times associated with this arrangement. And there's a whole bunch of other ones with this, and if you add them all together, it'd be every possible arrangement that you can have, you guys. Every possible arrangement. So, how many is that? Interesting part in its own right. I mean, that would be, how many of those would there be when you're actually doing that? Don't exactly have it in the notes, but I should. You know, nice to talk about right now, I guess you could say. If you were looking at this, how many times would this thing link up when you're doing it as you write it down? So every n to the 0 is 1, n to the 2 would be 4, n to the 3 would be 8, so it would be 2 to the n, 2 to the n power items. Now there's all coming out here. It's a little tough to kind of talk about. This is already telling you of the 2 to the n items. This is not one item. This could be 10. If there's I don't know how many would there be. Let's say 2 to the 3, 8, 2 to the 6. That'd be 64. This might be. You know, this could be a large number of those 64 items looking, 10 of them, let's say, could look like this. These aren't numbers set in stone, guys. Just to give you an example. There could be 10 of these or 20 of these or whatever there is, however it all plays out, looking for a particular R, like this. But if you added all the groupings together, this right here might be a value of 10 of them, 10 of these. Well, that's 10 out of the 64. Okay, so there's a lot to look at in that regard. We talk about it. It's the same thing here. Same thing here. I got it rewritten a little bit as well. What's interesting in is if you solve for Q, Q is equal to 1 minus P. If it's a 50% chance of success, 1 minus 50% is a 50% chance of failure. If it's 3/4, the probability is 3/4, which is 75%. 1 minus 75% is 25%. If it's 3/4, that's 75%. 1 minus 3/4 is 25% is 1/4. So if it's a 3/4 chance of success, it's a 1/4 chance of failure, so on and so forth. Now these binomial coefficients and binomial expansion are a special case. This thing that I'm talking about here, guys, is a special case of the multinomial theorem. And we're not going to go tremendously heavy on that, but and I think we've seen this stuff. We've crossed the bridge on this at one point or another, depending on when I've actually taught this to the classes that I've taught, or at least mentioned to them or pointed to it. But we've seen reference to this at the very least. All of what we're talking about so far, in some form or another, we've seen some kind of reference to it, at least with the binomial expansion and the multinomial expansion. So the multinomial expansion and multinomial coefficients, so let's see exactly how I want to say that. Let's just write it out. While we're doing that, you guys, this right here, this right here that we're looking at can be written as n factorial and the way they write that is, you can write it a number of ways actually, how you want to play it. Don't want to open too big a can of worms on this one, guys, because there's a number of ways you can look at it. But you can look at it n are like this, and that's combinatorics. I just said I didn't want to do this, I'm about to do it. That's the same as, well, in this case, yeah, when they're sort of complementary in a sense, that's true. The big thing, let's kind of leave that be for now. But basically, what it says is, if you got, if you're going to have n items or n trials of something, or n items, I guess you could call it, and you want to see how you can place our items, our marbles, our green marbles. There's our number of green marbles that you're going to put in n slots. The number of ways that you can do that is basically this. Block that off. If each one of those green marbles has a small number on it, that you can look at, say, yeah, there's green marble number 1, green marble number 2, green marble number 3, and the order in which all that takes place means something. Yeah, absolutely, it means this. You write it like this, and that's not the same as this. Forget all that. Forget everything here to the right, and just say, if I block this off, it's just this. True, if the ordering of, if those marbles are somehow marked and the order of those green marbles matters, you get this. If the order of the green marbles does not matter, bam, you got r factorial less of them. You got r factorial less of them when you do that. So, so that's pretty important in its own right, you guys. Let me just see here. I want to see if this is visible pretty well, guys. Yeah, it's okay. It's all right. It's visible okay. So it's kind of weird. If you wanted to do that with n minus r marbles, green marbles, believe it or not, you get the same amount. The same number of configurations that are independent of order. The ordering, those green marbles are indistinguishable. Those green marbles are indistinguishable from each other unless you really want to look at them closely. But we're saying we're not going to care. Just green marbles are green marbles. But if I do care, and it does matter the order, then you're knocking this thing down like this. It's a bigger number. Sure, that right there is not equal to that. It's equal to that times r factorial. This times r factorial. That times r factorial. So get that out of there unless you want to put r factorial right here and r factorial right there. But see, this right here is a bigger number than this when the order I just can't distinguish. I choose not to distinguish those green marbles. If I choose not to distinguish them, I got this. So we come to something like that. And that's the binomial theory. That's some aspects of the binomial theorem and binomial coefficients. We said that the binomial theorem and binomial coefficients are a special case of a very beautiful theorem and discussion that pertains to the multinomial expansion and multinomial coefficients. The multinomial expansion and multinomial coefficients is the general case for which the binomial theorem is a special case of the multinomial expansion and multinomial coefficients. So let's look at that. All right, guys, so, I guess this has been up here long enough. I always forget, like I said, that you guys can always go back and reference as much as you want when we're doing this stuff. So the binomial theorem is a special case of the multinomial expansion. Easy for me to say, right? The binomial theorem is a special case of the multinomial expansion. And the binomial coefficients are a special case of the multinomial coefficients. Okay, there's a lot here. I wish I could say a lot. I wish I could say all of the a lot that's there, but pretty fascinating stuff. I mean, if you were to take M items, rather. M as in mom items. X sub 1, X sub 2, X sub 3, plus dot, dot, dot. The whole thing taken to the n. That thing it's right, kind of in a basic sense, I guess you could say. Here we go. Here are the coefficients. K1 factorial, K2 factorial, K3 factorial, dot, dot, dot. There are m items. Yeah, there's going to be a Km factorial. The Km and the K3, for example, the Km and the K1, they could be the same number. They can, it happens. In various, I'll show you. Let's just kind of get to it. Then you got x1, k to the 1. These are all integers. Positive integers greater than or equal to 0. So not positive, just integers greater than or equal to 0. So I can't say they're always positive integers. It's had a lot to do when we were talking about, I think, Harvell and Pipe's discussion pertaining to Taylor's formula for multiple variables, for many variables. Taylor's formula for many variables, and we said, how does some of this stuff play out? How do they, a lot of that plays into the multinomial theorem. The way we're able to actually figure out what was going on with all kinds of derivation, all kinds of derivatives that were taking place, all kinds of exponentiation that was taking place, all kinds of exponentiation, both with operators and real number items alike. With everything that was there, operators and real numbers alike, when we're talking about a shorthand to discuss Taylor's formula for many variables, the multinomial theorem plays a big role in much of what we're going to discuss. So much of what you can discuss pertaining to that very beautiful formula associated with the formula for the exponential function, the formula for the base of the exponential function, e, et cetera, how you can do a lot of that stuff that's going on there. From Taylor's formula with multiple variables, with many variables, to talking about E, the multinomial theorem plays just a tremendous role in that process. Well, okay, we wrote this down. What a mess. There's a lot here. Yeah, it looks a lot like the binomial theorem, only if you thought the binomial theorem was kind of intimidating to look at, this is just more so, I guess you could say. So you look at this, and they're saying for any one of the k's, guys, all of the k's, I'm talking about the K1, the K2, the K3, all the way to the Km. K1, K2, K3, Km. For all of these, for all of the K subscript I, where I can be anything from 0 to n, K could be an integer greater than or equal to 0. Anything greater than or equal to 0 all the way through and including less than or equal to n. So that's all of these run the gamut. And you're going to see how many items are there. How many items are there? There's going to be a total of, there's m items taken to the n power, m times n terms are going to be present. The terms aren't going to be totally distinct. There may be, I'm making up numbers that maybe aren't really, I can say, entirely valid, but for our purposes, it's. I think the premise is, if there's m to the n terms, and that's, I don't know, let's say that's 5,000. Again, I'm just throwing numbers out there, guys, that may not have a basis in a lot of the reality of the mathematics, but the premise here is, okay, huge number, 5,000 terms total. 1,000 of those terms, let's say, if there's 10,000 terms total, let's say, 10,000 terms total, 1,000 of those 10,000 terms, or 2,000 of those 10,000 terms are identical terms. So there's a 2,000 in front of it, and there's some number, there's some x1, x2, x3, all multiplied. They're all multiplied together, exponentiated in a particular way. And I don't know, there's 10,000 terms total. Really? M to the n is 10,000, or some number that would actually work when we're talking about integers. You know, that's why I'm saying 10,000 might not be valid, but you get the point. A very large number. Yeah, within that very large number, there may be a large number of terms that are all identical to each other. 1,000 of those 10,000 may be identical. And we were saying that kind of earlier with the binomial expansion as well. So this is how it plays out. With the other one, with the binomial expansion, the m was 2, and you took it to the n. Remember, it was m to the n. So this right here, the m was 2. That's where we're getting it with the binomial. This is a more general statement of what's going on, you guys. Much more general statement as to what we're doing here. So on and so forth, guys. The k, the exponents, and I guess the number for which you're going to get the factorial, k can be anywhere from 0, including 0, all the way as big as n, and anything in between. And we also know something, though. There's some limitations here. And one of the limitations is this. The summation of all the ki's has to be of order n. In other words, if you were adding, k1 here could be 100, k2 here could be 300, k3 here could be 5,000. And all of them, the k1, k2, k3, when you add them together, adds up to 10,000. Adds up to 100,000. What is that? Well, that right here would be if you took all this to the 100,000th power. If you add all of these together, they're all going to add to 100,000. If that was 100,000. Let me make it easier. Let's put a 10 right here. If this was a 10, all of these would add up to 10. So all of the order of the polynomial doesn't change with the multinomial coefficients and the expression of the multinomial expansion, multinomial theorem. Okay? So we're summing each multinomial term, which looks like this. So basically, you guys, you're summing each one of them. This right here is a multinomial coefficient, and this right here is the coefficient times this guy. This guy might have a 5 right here, a 19 right here, a 55 right here, a whole bunch of different stuff. This guy might be 5,000. The whole thing might add up to the whole thing 10,000. Yeah, and this is the number of terms that look like this guy. The number of items that got this guy. All of these k's, when added together, add up to n. N, right here. They add up to n. Guaranteed. There's going to be a huge amount of diversity. What do you mean, huge amount of diversity regarding this? I mean, k1 is going to range from 0 all the way to n. k2 is going to range from 0 all the way to n. k3 is going to range from 0 all the way to n. That's a lot of stuff. Yeah, I know. When they do that, they're going to do m times n total terms. Some of the terms are identical. I didn't say they're all distinct terms. There might be 10 times x1 to the 19th times x2 to the 55th times x3 to the 5,000th. And they're the same. Oh yeah, there's 10 of them. There's 10 that got this. There's 10 of them that look just like this. This thing right here. How many look just like this? That coefficient will tell you. All those coefficients added together will come out to m times n. When you add them all together as they're arranging the way they're going. Pretty fascinating stuff. how that plays out. And like I said, it has huge significance when you're proving things pertaining to the immensely important mathematical reality used in mathematics and physics so often. That is the exponential function. When you're proving the exponential function, you're proving what E is. You're proving different ways of looking at something to the E power. When you're looking at Taylor's formula for multiple variables, many variables, all of it pertains to E. E has such special behavior, it's immensely important. Okay, so, well, okay, I mean, here I'm going to draw from some of the people about whom I spoke earlier, from James E. Turner's brilliant work, and they use different symbols, guys, than some of what I've already shown. So I'm going to just point it out, I guess, and then go for it, and then we'll just remember, we got to, let me just stay true to what he's doing, and then just know that, okay, there's different symbols there, so we can use the work that James E. Turner had done in his brilliant work, and then say, okay, this makes some sense. Okay, let's see what we can do. Okay, so let's see what we can say here, guys. Okay, well, again, James E. Turner's brilliant work, guys. If there's a binomial distribution, is there a mean to it? Is there an average value if you're drawing, if you're doing capital N number of trials and small n is the number of successes? Earlier I had R. Small r was equal to the number of successes, and small n was the total number of trials. Well, standard deviation and variance associated with the binomial distribution. Let's talk a little bit. Let's use the language of a brilliant person who's explaining some stuff to us. And since I'm using his work, let's use his language. So from James E. Turner's work, mu is the mean of the binomial capital N, I was using small n earlier, but we're going to use his language. Total number of trials. Either something works or it doesn't. We're not getting philosophical about this. It's a yes or no. Yes, success, no failure. It's one or the other. It's a yes or no answer, not a maybe. Okay, that's something we gotta stay with that when we're talking about this. For this binomial thing, it's going to be one or the other. Not both, not neither either. Okay, it's going to be yes or no, success or failure. N equals total number of trials. Then they say here, what used to be my R is James E. Turner's small n. N equals the number of successes. By definition, mu, the mean of the binomial distribution, by definition, they put three things here, meaning like equal and then some. You know, it's really equal. It's equal by definition. The summation from small n equals 0, meaning the summation of the probability of there being no success, plus the summation, adding the probability of one success, plus the probability of two successes, all the way to the probability of all of them being successes. You run the table with it. Here's small n equals 0 to capital N, and P sub n is the probability of one success. We're going to say, sometimes they just say it, it's a little confusing how it gets said sometimes, kind of leaves you to wonder a little bit, especially when you're first learning something like this. But I think it's just a good interpretation for us to say P sub n frequently, well, okay, let's just say P by itself, they're going to see it say P is one item. P is the probability of one thing happening. I mean, what is the probability of one success? Okay. What's the probability of another success? It's the same amount, it's P. What's the probability of two successes in a row? In a row? It'd be P times P. It'd be probability of success, the first draw is P. Probability of success for the second draw is P. Probability of success for the third draw is P. If you want to get 3 in a row, you're going to go P to the third. P to the third is the probability of all 3 happening. Yeah, that's not likely, but it's certainly not impossible. It's one of the possibilities. In 3 draws, what can happen? Well, in 3 draws, a lot of things can happen. I could get failure on all of them, which is Q, Q, and Q. I get success on all of them, which is P, P, and P. I could get, 2 of them successful the first time and a failure the second. Could be P, P, and then a Q right here. Or I can get Q and P, P. Or I can get P, Q, P. They all mean the same thing, and that's where you get the binomial coefficients. All right. So, I don't want to read too much into it, but this Pn is different. Pn is what is the probability of me having n successes out of a total of n trials? That's interesting. Pn, probability of n successes, well, here's P, that's one success. P to the n is n successes. Yeah, and the rest is failure, and that's capital N minus Q to the capital N minus small n. Notice you add these together, you get n. Right. And this guy right here, when we actually played it out, could say a lot of stuff is going on here, guys. Let me kind of look at it. You're looking at basically, you're looking at capital N factorial over, okay, let me just see here how I want to say that. There's a number of ways I can say it. Now, we said there's a lot that goes on here, guys. Just give myself a little bit more room. Capital N, so it's a lot like what we did at the beginning of the discussion, you guys. Capital N factorial, you're going to get capital N minus n factorial over n factorial. And the way they're going to write that is, that's going to be capital N, that's the combinatorics we were talking about. And again, it's this is stuff we've just seen this, and that's the same as that. And we did say there's a number of things that can happen here, guys. There's a number of things that can happen here. Okay, I mean, that's the deal here. There's a lot of this able to happen. How many have p to the n and q to the capital N minus n? How many have that? I'll tell you how many have it. Right here. That's how many have it. See, this is not just unique. There might be there might be 100 of these that look just like this. Yeah, they would happen in different places. You know, the NPs could have all happened right together. They could have been dispersed all over the place. How many different ways can I still get P? How many different ways can I get P to the small n times Q to the capital N minus small n? How many different ways can I do it? Right there. Your binomial coefficients. And that's where it's coming from here. That's in terms of P. Great. Well, I just told you what that was. And that's this, which is the same as this. Yeah, great. Now just throw an n in here, and we'll set up some mathematics, I guess. So if you're going to do that, it's right here. You're looking at it. You're going to see it again. We're just going to put all of what you just saw. We're going to put it right there. It's going to be right in front of the n. So what's going on? Well, what's going on is everything that's been going on, guys. I mean, it's not. Don't let this intimidate you too much. Here's n. Well, n's right here. Write it down. This p to the n all right, we just talked about it. Okay, in my notes, it didn't, somehow it got truncated, but I think I wrote it down again. Right, and it's there. It's written fine. Okay, so that's it. Well, that's mu. It's a long song and dance, but there it is. Fine, okay. Well, if that's the case, I mean, let's kind of sort of leave it at that for now, and then kind of I want to erase a little bit of this stuff. I don't want to be too all over the place with this. I only have a limited amount of the blackboard space, but at least we wrote it pretty loudly here. We got what we got. Can we use the mathematics with which we're rather familiar, I guess you could say, and see if we can talk a little bit? Okay, well, we said this here. It's going to come rather useful to us in some regard. Let me try. Let's try to talk a little bit more. We'll talk about the binomial distribution, number of trials, and everything. So let me erase this, and we'll start it. I don't want to try too much. I mean, let me just. I don't want to erase any of it, really, but you're going to have it in the written notes, guys, and you've got it on film, too. You can always come back in a sense, but again, the written notes are going to be okay. Well, okay. What do you want to say? What we know a good amount. I feel we do. I feel we're okay. Tell you what, they said take P, which is the probability of a success, and take Q, which is the probability of a failure. Put an X right next to the P. Add those together. Take the whole thing to the N. And man, we're going to need we need the binomial theorem, and we know how to do this. We've done the binomial theorem. This guy's kind of like this. PX is A, Q is B. Just make it one item. PX, make it A. Q, make it B. Go for it. Well, we've already done that. We found that to be the summation from n equals 0 to capital N. Okay, we've been down this road before. This guy's the A, this guy's the B. What does that mean? That means here's the A to the N. Here's the A to the N power. Remember, N is the number of successes. They use an R, what used to be the R. N is the number of success. This whole thing to the N power. And this other thing to the capital N minus N power. And we know this monkey business that they've been telling us. And let me just try to let's just try to see what we can say here. There's a lot we can say here. This is what it is. I said this is the A to the N, A to the small n times Q to the quantity big N minus small n times here. You get all this. I'm going to get all of them. How many are there? How many here are there? Well, we said it was M to the N, but M to the N, when we said it, N was everybody. In my terminology, not my terminology, other people's terminology as well, but the way Mr. Turner's describing the thing is, that's the capital N. M to the capital N. Well, if M is 2 items, 2 to the N, in our case, is going to be 2 to the N. We're going to figure out what that's going to be. All right, well, let's keep talking. The quantity px to the small n is p to the n, x to the n. Or, yeah, it's p to the n, x to the n, p to the n, x to the n, or x to the n, p to the n. Doesn't matter. Quantity px to the n is p to the n, x to the n, is x to the n, p to the n. I'm not saying anything too profound. We know that. Okay, sure. We do. And what else do we know? Well, we know this. If you sort of pull the x to the n away from everything and go x to the n right here, and this is capital N, p to the n, q to the n minus n. Hey, wait a minute, this looks kind of familiar. I mean, this guy, yeah, absolutely it does. So right here was the p to the n that we had earlier. That was a p sub n that we had earlier. That was the p sub n that we had earlier. Well, it's a little drawn out. Let me write it here, guys. Make sure you guys, I'm not sure what, the visibility is not always great. In the middle is the best, guys. I wish I had a little more room, but this is a very good setup. They worked very hard to get us here. So we're lucky in that regard. Small n equals 0, all the way to small n equals all of them successful. Small n equals no successes, all the way to small n equals everything is a success. Every single one of the big N draws is a success. Every one of them is. That's x to the n, p to the n. Yeah, it's absolutely true. Again, we're speaking the language that the people who are teaching us, that we have to agree with the language, guys. I mean, we don't have to agree with it, but at least momentarily, temporarily we do. Use any language we want to describe the reality. The reality remains what it is, independent of our choice of the language. The language just points to the reality. It's not necessarily the reality itself. You know, the language helps you look at it, but you can look at it a number of ways. I always talk about that with you guys. That's more of a communications class in its own right, but what some of the great scholars have talked about regarding that, okay? So, I'll tell you what. I mean, one of those great scholars, I think it was Alfred Korzybski, kind of talked about that, the principle of non-identity, reflexiveness, and non-allness. So how the limitations in language and how so the language is not really the reality itself, it points to the reality. Language itself is a reality, sure, but if I say that's an aircraft carrier, the word aircraft carrier is not the actual aircraft carrier. It's pointing to the reality of what the aircraft carrier is, etc. So it's kind of some interesting stuff regarding our choice of language and everything. So let's see. What I said is, given what we know, why not? Why not? Somebody might ask why. That's a good question too. Why? But we can also ask why not. This is a function of x. Sure it is. P is a constant, P is a constant, Q is a constant, and capital N for a given experiment, capital N is a constant also. X is the only variable. What is it? Well, I don't want to go there right now. What is it? It can be a lot. It can be any real number, actually. You probably expand it even further than that beyond the real numbers. We're not going there. For right now, let's just say this. Let's deal with the real numbers on this. If you take the derivative of this thing, small n equals 0, and small n can be as big as capital N. The small n could be capital N number of successes, or the small n could be 0 number of successes, or anything in between. Having taken the derivative with respect to x on each side implies the following. Let's figure it out. I wrote two things here, guys. Let's go. The derivative with respect to x of this is, I'm going to debate how I'm going to do it, I guess. By the power rule, bring this thing down, and you got px plus q, the whole thing to the capital N minus 1. And by the chain rule, you do the power rule first. You do what's on the outside first, then you do what's on the inside of this. The derivative of this, px plus q, is p. So that guy right there true. So what'd you do here? You did the chain rule. You did the chain rule. You did the power, by doing the chain rule, in this instance, doing the chain rule, you did the power rule first, then you did a derivative here, and you got, by the chain rule, you got all this, and then here you went inside by the chain rule, you got the p to come out here. All right. Sounds good. Yeah, that looks familiar. Yeah, sure does. Let's talk. I mean, we'll figure out what we're going to say about that. That NP, right? I think we talked about the NP earlier. For the life of me, I can't find it, guys. Let me see here. No, I saw it. Okay, yeah. Summation from n equals 0 to n. Summation from small n equals 0 all the way through capital N of small n p sub small n. That's equal to mu. We talked about that. That's the average. That's the mean of the binomial distribution. Fascinating stuff. What does that mean? Well, actually, I'll take that back. We're not quite there yet. We haven't. I take that back. This will have significance. Let me leave it for now. You'll see it. Let's go here. Here we are going to do the summation rule. When you do the summation rule, it is going to come out to from n equals 0 to capital N. And here we go. Start taking, that's a constant for a given instance. Yeah, we can debate that one. No, we don't have to even debate it too much. I mean, it's a constant for a particular instance, and I did not want to throw that out, but there it is. Yeah. Okay. Right. Let's see here. For a given value of small n and a given value of capital N, given value of small n, yeah, all this right here, and then ignore the x to the n. This right here, and then all this is a constant for a particular value. So let's see what we got. It comes out to here, guys. You do this thing. Look, I got it. This is not obvious, I guess you could say. Okay, you got this guy. We said he's here. And then we look at this, just ignore the blue thing right now. Ignore the blue thing. This times it. That's a constant for a given value of capital N and for a given value at a particular place of small n. Yeah, that's a constant. Therefore, if you're taking the derivative of a constant times this, which can vary, it's going to be the same constant, not touched, times the derivative of this, which is n times x to the n minus 1. And this right here is the probability. This right here, I don't want to, this is probably going to look ridiculous if I do it, but this right here, this stuff in the green, is the p sub n. Each one's a p sub n, you guys. So, I don't know, it's a little irritating to write it that way. But let's see what we got here. So that's, okay, so that's part of the, this is all p sub n. That and that. And that's different from this. This guy's not part of the game. But everything else, the blue stuff here, yeah, that's it. And all of that is the p sub n. Okay. N, x to the n minus 1, p sub n. What's p sub n? P sub n is this guy, not counting him. This times that, not counting him. That's p sub n. He's brilliant the way he did it. The way James Turner did this, you guys, was brilliant. Okay, there it is. You got this right here. Then they're saying, tell you what, if you let x, then you're done. You did what you did. Now just say, okay, this is true. I just want to be very careful how I talk about this, guys. I wanted to see what we can say here. It's absolutely true. We say it's true. Now, why don't you plug in a value of x? I got a good value of x for us to plug in, ladies and gentlemen. Why don't you plug in x equals 1? Really? Sure. I don't erase any of it, guys, I told you, but you guys got we can always go back with the film and see what we want. We'll put x equals 1 in there. I'll show you what I mean. X equals 1, huh? Put x equals 1 in here. Is that true? Yeah, sounds true to me. Px plus q, the quantity px plus q to the capital N power. If x equals 1, it's p plus q. Didn't we say that these are mutually exclusive events and one or the other has to happen? What does that mean? That means for sure one or the other is going to happen. The sum of the probability of something happening plus the probability of it not happening is for sure. Either it's going to happen or it's not going to happen. For sure one or the other will happen. What does that mean? That means p plus q equals 1. So, what does that mean? It means a lot. This is a mathematical reality. We know what it is. If you take the derivative, you've got this, and that's it. Yes. What is the derivative at x equals 1? If you put x equals 1 right here, and x equals 1 right there, it's just n times p sub n, summation of all those. And this is p plus q to the n minus 1 power. Well, p plus q is 1. 1 to the n minus 1 power is 1 times np. So what do we got here? So what happens, given what we just said right here, guys, just capital NP summation. Well, let's talk. I mean, make sure you're seeing what I'm doing here, guys. Put x equals 1 right here. X equals 1 right here. P plus q is 1. 1 to the n minus 1 power is 1 to the n minus 1 power is 1. NP is equal to the summation of all this stuff. What is going on here? NP is the summation of, and you put x equals 1 right here, summation from n equals 0 to capital N. it's not broke, don't fix it, right? I mean, so, I don't know. Small n to capital N. Wait a minute. This guy, way back in the day, was equivalent to mu. That's really important, really useful. Yeah, the mean of the distribution. Absolutely. Pretty important stuff. So that's what mu is. What is that in the language of what I was speaking earlier? The capital N with the language that we were speaking earlier is small n. And R was the number of successes, remember? And small n was the total, the total, which is now capital. They call it capital N right now. I was calling it small n. So this would be small n times p. And we've seen this, you've probably seen this before. Nice little proof of it. The person, again, Mr. Turner, who had done this, perhaps Dr. Turner, I don't know who the gentleman is, but pretty amazing stuff. The mean of the binomial distribution is mu equals NP, capital NP. The mean of the binomial distribution is mu equals capital NP. Now we consider the variance and standard deviation. So let's figure it out. I mean, now we're going to, at this point, we're going to find sigma squared is the variance, and the square root of sigma squared is sigma, and that's the standard deviation. Okay. Pretty fascinating stuff. Now we had the stuff up there. Just remember, okay, so let's see. We drew some conclusions here. We remember the conclusions we've drawn, and then we'll put them all together. We know, now we consider the variance and standard deviation of the binomial distribution. Let's start with the variance. The variance is sigma squared. Okay. Variance is sigma squared from n equals 0 to capital N. How does that play out? Well, from small n equals 0 to small n equal to capital N, here's a small n, here's mu. We've already talked about that. for the binomial distribution. We know what mu is. I mean, we already wrote it down. I'll write it down again. I don't want to clutter things too much. You've got it. We got it on the tape. We got it in the notes. That right there times the probability. The probability of n happening. Very important. What's going on here? Let's talk. Okay, let's go. Square this thing. -2. Yeah, absolutely true. Can we write it a different way? Yeah, why not? I mean, let's just take that p sub n and bring it in there. Again, it's got to be a summation though. So everything's kind of not a big deal, but just make sure that it's everything's being summed up. So you're talking about a lot of different scenarios here. They're going to play out, but what we got here is n squared p sub n. The p sub n comes inside. N mu p sub n plus mu squared p sub n. True. There's a lot of ways you can go. I'm not sure one's any better than the other, but I think I trust the way these people have done these. They know a tremendous amount, so I trust what they're doing in the mathematics that they're presenting. So we got this right here. Let's do a whole bunch of summations here. Let's break this up into a number of summations. Try to speak the language. Mu is a constant, so is -2. Mu is a constant, so is -2. And the other one is correct. Mu squared is a constant. Yes, true. We got to talk. Let me get some chalk as well, guys. All right, guys, as we said, we got to talk a little bit. You guys remember this. We remember that the summation from small n equals 0 to capital N of small n p sub small n, that right there, this right here, guys, the summation from small n equals 0 to small n equals capital N of small n p sub small n, when you sum that, that's mu. That right there is mu. This right here is mu. Mu times mu is mu squared times negative 2. Negative 2 mu squared. Got a mu squared right here. We also know that the probability of there being 0 successes plus 1 success plus 2, the probabilities of all the different success possibilities has to add up to 1. You're for sure going to have something happen. What do you mean? You're for sure going to have no success whatsoever out of capital N trials. In capital N trials, you might have no successes, small n equals 0. You might have small n equals 1 success. You might have small n equals 2 successes. All the way through the gamut of small n equals capital N. All capital N trials might all be successful. You might have capital N successes out of capital N trials. All capital N trials were successful, or that's capital N. Or none of them were successful, and everything in between. Well, it's got to be something. It's either complete failure, complete success, or anything in between. If I add all the probabilities of all the possibilities, there's no other possibilities left. So whatever the probabilities are, when you add them together, one of those things is going to happen for sure. Therefore, the sum of all the possibilities has to be 1. So this guy is 1. This guy is mu. And when we do the mathematics, just think it looks a lot better over here, guys. You can see it a little bit better. So I'm trying to, again, we know where this stuff is. We can always come back to it. What is it? Well, okay, we'll see what it is. Sigma squared is the summation from n equals 0 from small. Sigma squared is the summation from small n equals 0 to small n equals capital N of small n squared p sub n. Okay, it's a little bit of a challenge, but we'll talk. We'll talk about it. This ain't bad. That's mu. That's 1. Mu times negative 2 is negative 2 mu squared. That's 1 times mu squared. Okay? So this is 1 mu squared. This is negative 2 mu squared. Put a plus right there. I like to add. Whenever you subtract, whenever in doubt, add. 1 mu squared plus negative 2 mu squared. 1 mu squared plus negative 2 mu squared is negative 1 mu squared. Plus a negative 1 mu squared or minus mu squared. All right, we can debate that. True. Now Turner tells us to come back to what we had earlier and take a second derivative of the quantity that we had earlier with respect to x. So, see what he's doing here. He's telling us, okay, we did all this, guys. We got all we got. Leave what you got. Again, you don't like to erase all of it. You wish you had a lot of blackboard, I guess. But you're limited on that. They're saying, okay, well, let's see what we can derive. Can we say anything here? Can we say anything here? Just checking if the sound quality is okay, guys. I think we're okay. All right. Okay. So what are we doing? Well, let's go back. Let's go back to what Turner was telling us, guys. Brilliant stuff, as I said. Very ingenious. I don't know if he got this from somewhere else or if it's something he's gone into on his own. Either way, it's just brilliant stuff. Good stuff for us to look at. We talked about this, and again, we're coming back to things that we've done. Got this. A little easier to look at when you write it like that, now that we see it. Pn x to the n, capital N minus small n. Right, it's everything we've done in the past. Okay, let me see exactly where we want to go. I want to kind of be consistent with what he's talking about. You guys know the game. I mean, we saw this guy here when we were doing what we were doing. Absolutely, we know that. When we know, no, that's absolutely true. We know that is the summation from small n equals 0 to capital N of x to the n, just bring the x to the n out of there. Now we've done this, forgive me for doing it again, guys. This mess right here is P sub n. Here's capital N. That's P sub n. Okay. We have been there. We've done that. Yeah, we know all that. We know all that's true. Now, Mr. Turner's telling us, and take the second derivative of this quantity with respect to x. So we've got, here we go. This is what we dealt with originally, right? Which is the same as this. P sub n is a constant for a given value of small n. For a given value of small n, this is what P sub n is. So be careful. Which is good. Be careful, and also it's fortunate that that's a constant. It's a constant for a given value of capital N in the experiment, in trial. It's a constant for a given value of capital N and for a given value of small n, and for a particular P and a particular Q that remains throughout. Okay? You've got all that, guys. Let us go right here and take the second derivative. I know we made x equal to 1. I get it, but I'm not doing it now. I'm going back as though x is not equal to 1. X is something. X is some variable. And then I'll plug in x equals 1 when I choose to do so. Be careful there, guys. Go for it. It's a lot to say. Let's see how I'm going to say it, guys. That's the same as yeah, it's true. Okay, we've said a lot. It's right here. Let's actually do it. Let's do it, and let's remember some things, and I think we're going to be in pretty good shape. See what we got. Let's do it. Let's do the chain rule twice. Let's do the chain. We're going to do the chain rule. We did the first derivative. First derivative, the capital N came forward like this. This was to the n minus 1. Capital N came right here. First derivative, capital N came over here. Then there was the whole thing. Capital N times the whole thing to the n minus 1 times p. Because you did the p. Then do it again. So when you do it again, it's going to be, so do the derivative here patiently. P comes out and P comes out again. Okay, true. And here, it's going to be the summation from n equals 0 to capital N. First derivative is nx to the n minus 1. Pn's a constant for a given place. Second derivative is second derivative is going to be the n minus 1 comes out. X to the n minus 2, P sub n is right here. Okay. That's all that. Yeah, you've seen it. Again, it's a little tedious. I jumped forward a bit, but I know you guys can do this. I know that you guys can do this. Just take the second derivative of this. It's going to be the chain rule applied twice. Chain rule applied twice, it's going to be a p and a p multiplied with a p. P multiplied with p is p squared. This comes down, there's an n. The n minus 1 comes over as well. Left with n minus 2 right here. Looking good. Again, the chain rule applied twice. P times p is p squared. This comes out from how we know how to do a second derivative and how we know how to do the power rule. Power rule's applied here, and you got this. Yeah, true story. So they want us to remember a couple things. We're going to remember that P plus Q equals 1. P plus Q equals 1. We're going to set x equal 1, which will really help us out to talk about this kind of thing. X equals 1. And we do remember that the summation from n equals 0 to capital N P sub n is equal to mu. What's going on here? Well, lots going on here. You're looking at what you got. You're looking at what you did. If you put x equals 1, if you put x equals 1 right here, x equals 1 times p is p. So x equals 1 times p is p. P plus q is 1. 1 to the capital N minus 2 is just 1. So that we just got, after you do that, you put x equals 1 right here. X equals 1 right here. You got p plus q, which is 1. 1 to any power, or at least for our purposes, x equals 1. 1 times p is p. P plus q is 1. 1 to the n minus 2 is 1. And you got this right here. You've got capital N minus 1 p squared equals, put a 1 right here, one right here, 1 to the small n minus 2 is 1. 1 to the small n minus 2 is 1. You got small n times small n minus 1 times p sub n, summation from n equals 0 to n. N equals 0 to capital N yeah, that's true also. Then they say, okay, take this guy right here, and you can break this thing up. You got n times n is n squared, n times 1 is n. You got n squared p sub n minus n p sub n. Which is equal to n squared p sub n minus the summation capital N of n p sub n. So, sorry guys, I got equal signs all over the place here. But that's a good sign. They're all equal. They're all equal. This one came down, I mean, I said we came down here. True, but all of this is equal to this. I mean, let's make this really clear. All of these are equal to each other. This thing right here is equal to this thing right here. Yeah, I mean, this is equal to that, is equal to that. And that right there is equal to this. So this and this are equal. Yeah. I mean, when you're doing it in your head, guys, or doing it on pencil paper, it's not quite as convoluted and kind of all over the place when we're doing it. But make the long story short, I mean, you could have made the jump right here. At this point right here, you could have just said, hey, look, guys, hold on. At this point right here, n times n, small n times small n is small n squared times p sub n. You're summing all that. Well, small n squared, p sub n, you're summing all that. Because n times n, or small n times small n is p sub n. Small n times p sub n is small n squared p sub n, and you're summing all those. That's this guy. And this guy is just n times 1 times p sub n. There's a minus here, so it's minus n p sub n. That's being summed. You could have jumped from here. You could have jumped from here to there without going here. So this guy, this is equal to that, true, and from that you go right to this. So anyway, that's the big thing. You've got all this, and you've got all this. That's where we're going to play the game. Well, okay, we got to remember a couple things now. The summation from small n equals 0 to small n equals capital N of small n p sub n, that's mu. And the other guy is, well, I guess we'll figure out what it is eventually. But so this right here, that's mu. So it's minus mu right there. In fact, right here, there you go. I mean, what are we talking about? I'm making a big deal out of it. We already wrote it down. It's right here. So that's mu. So what do we got? What we got is capital N times capital N minus 1 let's see what we got. Again, guys, if it's not broke, don't fix it, right? I mean, we got this p squared and the other one, that's that whole song and dance. Now, we already said what this was. Here's the minus. Don't worry about the minus. Worry about this. Summation from small n equals 0 to small n equals capital N of the quantity small n p sub n, the summation from n equals 0, the the summation from small n equals 0 to small n equals capital N of small n p sub n is mu. True. You're wondering how it's going to, well, it ends pretty soon, you guys. Now, we had already kind of gone somewhere. Yeah, right. We write it down. We had earlier, remember we had drawn some conclusions. Remember, we've done stuff. I mean, we were, we know a lot. We were there a little earlier. Let's talk a little bit. Remember, we said earlier, from n equals 0 to capital N, of, I think we have, let me just use the exact same n minus mu. I think that was it. It was that simple, I think. No, it was that, and you're summing it. So you're kind of saying, how many successes are there as we go. So what you have is, right, this is kind of interesting how it plays out. This p sub n, it's a probability. You can kind of make it into a fraction if you wish. And you could say that the bottom thing is the denominator, and that's the total number of trials out of n. And the other one will tell you how many times is it successful. Could be could actually be a decimal, for all we know. The whole thing. I mean, even the top of the fraction, the numerator, could be a decimal as well. But let's put capital N on the bottom, and when you're adding all those, the most they can be is always up to n. So that's pretty crazy stuff in its own right. I mean, you could kind of, this thing already contains like division by this already has in it division by the number of trials. It has division by the number of trials already in it. And then the bottom part has division by the number of trials already in it. And the top part has the number of times this occurs. The number of times this small n for a given small n minus mu for any given small n minus mu squared, how often is this quantity occurring? And that's the numerator of this p sub n. And the denominator of the p sub n is the total number of trials that are taking place from n equals 0 to n equals n. Yeah, sure, it sure works okay. It sure, in other words, you can take it as though you were saying the number of times it's occurring divided by the total number of times it's occurring, but you can divide by the total number of times it's occurring at the very bottom and still get this. It works. It works just fine, guys. This is fine. The way they got it set up is beautiful. It works great. What we can say is, when we look at it, For the life of me, I can't find it now. Okay, there it is, right. When we were doing that, I just want to go back. Forgive me for digressing, but I know you have it on film anyway, but I think now is a good time to kind of go back, explicitly go back. And they're saying that's really what it is. And if you do this, you've got the summation from n equals 0 to capital N, and here we go again. Yeah, it should look the P sub n. Just let me try to write. Okay, I just wanted to come back because you can see it's here. The P is here, P sub n is here, and P sub n mu, and mu squared P sub n, okay. Well, right. Let's still leave it there, guys. Again, is it looking familiar? Yeah, it should. We've already done it. But like I said, this is a good place to digress, I think. N equals 0 to capital N, n squared P sub n. Okay, that looks familiar. Yeah, it should look familiar. It's right here. And this guy right here, negative 2 mu n P sub n right, the negative 2 mu, you got that. And this one's right. U squared okay. Well, that was 1. 1 times mu squared is mu squared. This is mu. So mu times mu is mu squared. So it's negative 2 mu squared. And this is a bit of a mystery, but let's leave it as a mystery. At least for now. Summation n equals 0 to capital N of n squared P sub n. We'll figure out what that is. This whole quantity, summation from small n equals 0 to capital N of n, summation from small n equals 0 to capital N of small n P sub n is mu. Mu times mu is mu squared. This is negative 2 mu squared. This right here is 1. Times mu squared is mu squared. Mu squared plus negative 2 mu squared is negative mu squared. Mu squared plus negative 2 mu squared is plus negative 1 mu squared. Or plus negative 1 mu squared is minus mu squared. Okay. Yeah, we know that. We didn't have to do it again. We could have just looked at our notes because we already derived it. But I think it's, whatever. We can argue it either way, I guess. But there it is. We've got this. Is there something can be said here? Yeah, there is something can be said here, guys. This whole song and dance, mysterious as it is, that thing right there is equal to, well, if you add a positive mu squared on each side, mu squared plus sigma squared equals this guy. Mu squared plus sigma squared. Let me see the number of ways I can do it here. Right. Okay, we got this. Let me see exactly what he was doing. I don't want to do anything too careless. I've taken a good portion of your time already, guys. Let me try to. Okay, we've done all of this. Okay, you're wondering, okay, so what? What is he doing? What's the big deal here? Okay. I got it. I think the way we can do it is, okay, let me try to see exactly, for some reason here. For some reason, I think I did something that I should not have done. Right. Okay. No, I think I'm okay so far, guys. Let me do something here. Let me add a positive mu on each side and then get this guy by itself. N equals 0 to capital N. N equals 0 to capital N. Summation from n equals small, from small n equals 0 to small n equals capital N squared p sub n. Add mu on each side. Plus mu. Okay. True. Okay, all we did was mess with this, and it was okay. I was a little afraid for a moment, guys, that we hadn't done everything here. We did. And this guy right here, I mean, there's a number of ways it can be written. So sigma squared, you guys, sigma squared equals the summation from small n equals 0 to small n equals capital N of small n squared p sub n minus mu squared. Yeah, true. There's a number of ways we can do this. Why don't you get this guy by itself and see what you can do? For some reason, I think I did the same thing, guys, to be honest with you. Right. This right here. So let's take, I don't know, I think I showed it a little differently. I think it's a horse apiece, guys. Let me take this guy and write it as leave this guy as is, add positive mu squared on each side. Add positive mu squared on each side. For some reason, I think I did it a little bit differently, but I don't want to sit here and delve into it too much. It's the same, you're going to get the same conclusion. What you get just try to see here, guys, what I'm doing. For some reason here, let me just see. Right, they're just saying the same thing I am about to say. Mu squared. For the life of me, guys, I'm looking at it. I'm just trying to. So, okay, so you got it to here. Sigma squared plus mu squared is what this guy is. Sigma squared plus mu squared yeah, I mean, you can look at something like that if you want. Yeah, it's basically what I had done, guys. So, don't want to erase anything, but okay. We've done a lot. A lot of it we'd already seen, guys. We could, if you're comfortable with the notes you saw in the past, deal with it. It should be pretty good. I wanted to kind of go a little bit further. And there's a lot of ways you can set it up at this point, but I would do this. I'd say, okay, maybe we luck out, maybe this thing works out. I mean, that's kind of the goal when we're doing this. Sigma squared is that. You got n minus 1 p squared plus mu minus mu squared. So that's kind of a little bit roundabout, guys. You could have done this without doing some of the stuff I did earlier, but you want to get to here. This comes out to n squared p squared minus n p squared minus mu plus mu squared. Capital N times P is mu. Capital N squared times P squared is the same as capital N times P, the product squared. Well, capital N times P is mu. This is mu squared. This is N times P. That's mu times P. This is mu. And this is mu squared. Mu squared, I'm sorry, that was a minus right here, guys. That's a minus. So this is a minus. So this is a minus. Minus mu squared and positive mu squared are gone. You know, this is plus a negative mu squared. Gone. Positive mu squared and plus a negative mu squared. Gone. sigma squared equals minus p squared. This was a plus mu, you guys. Sorry about that. This is a plus mu. That's a plus mu. That's a plus mu squared. But subtract mu squared on each side. You got a negative mu squared. Mu squared, negative mu squared, and positive mu squared is 0. That's this guy. This guy was already here. He didn't move. That's a plus mu, you guys. That's a plus mu. So that never should have, sorry about that. That's plus mu. All right. Sounds good. Sigma squared equals mu plus a negative mu p, or minus mu p. That's it. That's interesting. That in itself tells us a lot. Plus a negative mu p and a positive mu. I'm sorry, guys. This was always, on the right-hand side, that was always a positive mu. Positive mu on the right-hand side. Positive mu on the left-hand side. We subtract a positive mu squared on each side, then it's minus mu squared. And that was minus mu squared and plus mu squared is 0. The plus mu was always there. I don't know what I was thinking when I did that. All right. Then, at that point, you guys, pull a mu out of there, pull a mu out of here, 1 minus p. Well, wait a minute. Isn't mu capital N times p, and this is 1 minus p. Isn't 1 minus p equal to q? 1 minus p is equal to q. And there you go. That was it. Yeah, you play the game here. These are the big ones, guys. I mean, once you bring it to here, just don't make any careless mistakes that I essentially made, but luckily caught. And you get to here. And there's your way of looking at it. Maybe it's a little easier to look. I don't know how good the camera quality is. Pretty good, guys, but just in case. You did all that stuff. I mean, like I said, you did bring it to here. Once you brought it to here, maybe it's just a little easier to look at. We were able to get it to here. And that's the end of the story right there, guys. If you can bring it to there, pull a mu out of there. We already discovered a while ago that mu was capital N times p. One minus p is q. You've got it. Sigma there it is. So you got that, and you got this. Now again, guys, we use small n to mean all the trials, so it'd be small n PQ. if we were using the language we used earlier. Small n PQ, if small n is all the trials. Square root of, the product small n PQ, if small n is all the trials. For us, small n was not all the trials. Small n was each individual number associated with the trial. So there's going to be n trials, and how often are there going to be that many successes associated with that? From 0 successes to capital N successes, and from 0 to capital N. From 0 to capital N are the values that small n could take. Earlier, in another use of language, small n was the equivalent of the capital N, the total number of trials, and R was the number of successes. So it can kind of go, look out for it. I mean, the language works out like that sometimes. The different language gets used sometimes, you guys. And I go into it, I talk about it a little bit. It doesn't, that's not the big thing. You could write it with a small n in front or a big N in front, as long as you're speaking the language of the problem, the language that is being used to get this job done. So these are it. At the end of all that, you guys, we did, just write this and I think we're done. Given the language that James Turner had used to do this, let's stay consistent with that. Let's use that to kind of give the answers to what we're doing here. So as we said, forgot how to write the letter Q, guys. Sorry about that. There it is. Yeah, looks good. Just make sure. Last thing I want to do is make a careless mistake on this. Yeah, looks good, guys. That's what you're looking at, and that's a look at some of probability theory. We'll look at more, obviously. I mean, in some sense, this stuff kind of, but this is pretty fundamental stuff that gets us to the other stuff that we want to do, that gets us to some of the other mathematics that we want to do. It's a look at some probability theory, and then this helps us take a walk toward the normal distribution when we're doing this stuff. All right, guys, thank you so much for your time. All the best to you.